చెప్పినా రమ్మను ఒకసారి తొందరగా. లోపలికి వెళ్ళి కొంచెం వైట్ పేపర్లు తీసుకురావాలి. ఇక్కడ లైట్ వేయాలి కొంచెం. హెచ్చమా! హలో! ఆ! 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 ఏం రిసెట్ అది? హుహు. ఓకే. ఎంత అయింది ఛార్జ్ ఏది? ఓకే. ఓకే. ఎక్కడ మామూలుగా ఆన్లైన్లో చేసావా డైరెక్ట్గా? ఓకే.
Yeah, so yeah, my screen is visible. The sound is on. Okay, then we'll start. Uh, Actually, I muted one participant before, but now you can talk. It's okay. So, yeah, so basically, today, I mean, this is just an introductory week for convection problems or various aspects related to the convection uh, problems. I think in week 5 we will talk like more details about boundary layer, etc. But right now we'll do some introductory problems because that was mostly what was covered in the class. And if I look at your assignment also, so we'll solve similar problems, but going forward it will be more involved discussion on the boundary layer. But right now, since it's the start of convection, the most important parameter in convection is if it is a thermal convection, it is heat transfer coefficient. If it is mass convection, it is mass transfer coefficient. And similarly, in flow and all, uh, they basically call it momentum transfer, etc. That's where this boundary layer, etc., comes into picture. But maybe we'll discuss about that later. So let's focusing on this week's content. So what all was covered in this week's? I mean, by this week I mean week 4. So if you look at the lectures, first was on introduction to the convection heat transfer, then discussion about heat and mass transfer coefficients, then brief introduction to boundary layer. So there are three types of boundary layers. First is thermal boundary layer, then concentration boundary layer, and then momentum boundary layer. So all these things were introduced. Then basically discussion on the boundary layer is started with some approximations and governing equations, but we'll take those maybe in the next class. So right now we'll start with some basic things about the conduction, etc. Convection. So let's take first problem, which is, you'll see this type of questions from this topic a lot. So okay, we'll start. So this is previous year GATE question. So it is mentioned that for a flat plate, non-dimensionalized or non-dimensional fluid temperature profile near the surface is given by, this is wall temperature, this is the temperature near the wall, and non-dimensionalized by the temperature difference between wall and the far ambient. It is nothing but a quadratic profile of non-dimensionalized distance from wall, which is y by L. So y represents the coordinate in which, y coordinate in which heat transfer is taking place, and L is the length of the plate. So the question is asked, if thermal conductivity of the fluid is K and wall heat flux is Q double dash, the Nusselt number Nu, which is given by this formula was given in the question itself. So L by K is equal to what? So this is the question. So here you may not know Nusselt number so far because it is not yet introduced to you, but basically for now you can understand it is something which relates to the ratio of heat convection to the heat conduction, something like that. So when it is very high, that means the heat is convected more as compared to conduction, and it is, when it is of the order of 1 or so, it is basically conduction and convection are equally dominant phenomena. So before solving this, since we are talking about convection and it's a flat plate, typically you'll have this type of problems. So you should know some things before you solve the problem. So typically, okay, I'll just move it slightly here. So what happens as you can see in this question also, so whenever there is flow with some velocity and some temperature T infinity, and let's say this wall temperature is TW, in that case there will be momentum boundary layer which will be shown something like this, and this will be your free stream velocity at this point, and then there will be some thermal boundary layer because of the temperature difference between the two. And since here T wall is greater than T infinity, you can get that idea from this from the denominator here. So the scaling is done with respect to T wall minus T infinity. So actually you can't say anything like that, but let's say it looks like this. It is something. Alright. So you will have this thermal boundary layer. So this is your momentum boundary layer. This is your thermal boundary layer. And in this problem, there is no concentration boundary layer, but there can be. So basically, this image you would have seen a lot of times. But there are some things that you should know. Essentially, it is an interview question. What they ask is what is convection. So basically, it is conduction at interface plus advection in the bulk. So uh, from here only the name conduction is, I mean convection had come. So CON from here and vection from the advection part. So basically what happens, first the heat from the bottom wall is conducted to the first layer which is at the rest because of no slip boundary condition here, and there is a conduction, and once the conduction is there, then because of the fluid motion the conducted heat will get advected, so it will not stay at the same place, it will move because of the bulk motion of the fluid particles above the plate. So that is the primary definition, and this is first thing that you should know, uh, because that's very standard question in any interview. They'll just ask you what is convection, and you prepare so many things, and when somebody asks you some basic question, you get stuck. So anybody asks you what is convection, you could say that it is the mode of heat transfer where there is a conduction at the interface between solid and fluid which is in motion, and then the conducted heat gets advected because of the bulk fluid motion, and that's how the convection heat transfer takes place. Typically, if it is a forced convection, the convection will give you very high rate of heat transfer, and that is why it is preferred. So wherever you need to take out the high rate or to supply heat to any substance or surface at very high rate, there typically forced convection is used. And in some places where the heat transfer rate is not that high, you can use natural convection. So I'm talking about very vague terms here, high, low, and because this is an introductory class. But the point is, we'll talk about those later also when we'll discuss them in detail. So that is one thing. Yeah, one more thing is typically this is also asked, and this is again maybe we'll talk about it later in boundary layer concept. But this is regarding the shear stress. Actually, this was I think directly they had asked this problem not for a flat plate, but for a pipe flow. I think one of the previous gate exams, what they tell is, let's say this is like a boundary layer, uh, typical U infinity, T infinity. This is your flat wall temperature. This is your flat plate. And the question is something like this. I'm modifying it. It's not exactly how it was asked, but for the sake of argument, I'll modify it. So there are two sections. So this is your section one, and then at some distance, which is significantly away from your starting edge, there is section two. So what the question was that uh, you know what is the this thing, yeah, so and this is your x and y coordinates. Typically these are the x and y. I'll not define it everywhere, but this is the accepted convention, that this is your x and y coordinates. So the question was uh, yeah, so question is basically, is del t by del y y equal to 0, but at section 1 is equal to del t by del y at y equal to 0 at section 2. So basically what they are asking is at the sorry at the wall. So basically here at y equal to 0, the temperature gradient with respect to y direction, where it will be, whether they will be equal or different or how. So typically what happens for this type of problems, you can't solve them mathematically because that will be too involved. You need to rely on your gut feelings. So what happens, if you notice here, let's take the section 1. So here you can see, if I so how should I say, so what happens, there is small height of boundary layer, right? The boundary layer is just starting to develop. So here T infinity is there and here T wall is there, and this distance is pretty much smaller as compared to section 2. So therefore you have to get the delta T of T infinity minus T wall with this small length. So basically what I'm trying to say here is, if you consider this as y1 and this as y2 length, here your del t by del y essentially corresponds to uh, delta t divided by y1. Delta t is nothing but t wall minus t infinity. I should write directly t wall minus t infinity. Okay, and here your del t by del y is nothing but determined by t wall minus t infinity, same delta t, but at y2 distance. And since y2 is greater than y1, the temperature gradient at the beginning will be higher. So you should, if you don't understand this explanation, or if you forget uh, during your exam also, no issues. You shouldn't. You should remember the answer. So the answer is they are not. They are not equal, because if they are equal, then there won't be any boundary layer. So the correct answer is uh, initially the gradients will be higher. So yeah, so basically correct sign is greater. And this happens not only in flat plate, this happens in pipe flow also. Maybe we'll talk about this later when we uh, you know talk about boundary layer more, but this is very important thing that is not told usually. And when you see such problems directly in gate exam, you can't solve them by mathematics because it all depends on your intuition. So I'll just repeat once again and then we'll go back to our problem. So here you have to get same delta T between plate and the boundary layer end with short distance, whereas here you have more distance to get same delta T. So therefore, when you have large distance in y direction over which you want to get same delta T, the gradient at that section will be smaller as compared to the gradient at the inlet. And by that logic, gradient at the start will be very high. First of all, because the length scale here is almost approaching 0. But typically what they do, they assume, they assume that, I mean, this is not, see, basically, the correct way to say is that at y equal to 0 and x equal to 0, which is the starting point of the plate, there exists a singularity. There you can't say, you know, uh, because the gradients will be too high, because y is almost 0, right, at this point. So del t by del y will be very high. So to avoid that complication, what generally accepted convention is, you just say that the boundary layer starts from very small distance after 0. So if this is your 0, 0, boundary layer starts from, let's say, 0 plus, very small distance after 0. Okay, so that is also one thing that they ask, but not frequently, but you should know. So coming back to this, we'll focus on the question. 1 second, give me some. Yeah, so coming back to this question, so now, uh, you know, mm, yeah, we can look into that here only. So there will be conduction from the wall to the bulk of the fluid, so that will be K del T by del Y at Y equal to 0, and same heat will be getting convected from the wall to the bulk. So this is the general heat balance or energy balance that is done, and that is what we are going to use for solving this question. And this was done in class also, and you can understand, right? So whatever heat is coming, same is going out via convection. So therefore, what you can say is the heat flux per unit temperature difference is nothing but H, the heat transfer coefficient, and this is a local heat transfer coefficient. So uh, keep that in mind, because there is an average heat transfer coefficient also. We'll look into that next. So here, see, I just wanted to give you the introduction to the Nusselt number, because here they talked about Nusselt number, right? We have not yet discussed it, but you can see this is nothing but local heat transfer coefficient, and therefore you can just say that Nusselt number, this is a local Nusselt number, is just nothing but HL by K, and K is of fluid. So remember, this is K of fluid. If it is K of solid, that is in lumped analysis that we did in last class. So this is the definition of Nusselt number. We'll talk about it later also. For the time being, let's continue and solve this problem. So essentially, what we need is we need uh, flux per unit delta T and Lk. And now what we have is our temperature profile. I'll just copy it here so that when I take the gradient, it will be okay. I should not have done that. I should have copied it. So from here, if you take a gradient del T by del Y, what you end up with is this 1 by T wall minus T infinity remains, because it will be same, and since T is in the minus T, then there will be minus 1 here. A goes to 0, B into 1 by L plus 2C into Y by L. So this is your this thing gradient, and at Y equal to 0, this term goes to 0. So what you are and what you left with is del T by del Y at Y equal to 0 is nothing but yeah, you take minus sign here, and then this TW minus T infinity will go here, and this is just B by L. And we know we also have the flux basically is conducted by conduction at the wall. So put that gradient sign here, so you basically end up with BK T wall minus T infinity by L, and we need to find Nusselt number, which is nothing but heat flux per unit temperature difference into L by K. So now put this flux value here. So this TW minus T infinity gets cancelled. So what you end up is BKL into L by K. So basically you have constant Nusselt number, which is equal to B. So this is the answer, but the point is you should appreciate this very important energy balance, because you use this multiple times, not only in this question, but there are some variations of these questions. I think one of such variation is asked in your assignment also, I think. We'll see. Okay, so that is one. So here your Nusselt number is constant, and again, you know, Nusselt number essentially is HL by K. L is constant, K is constant, so that means your H is also constant. So this is a case of constant heat, constant Nusselt number that translates to constant heat transfer coefficient. So your local heat transfer coefficient is constant here, here, everywhere. So that is one more insight that you can draw out of this. Now, yeah, there was another question. I mean, we'll just think on it. So similar question. In this question, uh, this is also previous year gate question. Similar question was there, and only what they did, they changed the temperature profile. So in this case, the temperature profile was given like this. So they had 3 by 2 y by L minus 1 by 2 y by L cube. So we are not going to solve the same thing, because the only thing is this: if you when you take the gradient delta t by del t by del y, this will be your remaining term, and this will go to 0 at y equal to 0. So here basically this 3 by 2 is nothing but your b. So then you will get nu as equal to 3 by 2. So like that. So similar, I mean, I can frame like many questions similar to this, but you get the idea, right? What we are trying to do here. Then, hmm, typically what happens, it's not mentioned here, but this Nusselt number, in this case, it came constant, but as you can guess, it will not be constant always. So we'll discuss this in next class, but what they typically do is some experiments are done for certain set of boundary conditions and initial conditions. Not initial, only boundary conditions, because we typically deal with steady state problems here. Uh, and what they do, they come up with some sort of expressions for Nusselt number, and that will be function of some 2-3 parameters, such as flow velocity, density of the fluid, dynamic viscosity, kinematic viscosity, all those things, and then you get a correlation for Nusselt number as some function, and you directly use that, and you get HL by K as the Nusselt number definition, and then you get the H. Basically, that is how the standard process is. But we'll not discuss that today. We'll discuss it in the next class. So that is that. Then yeah, yeah, there is one more question. Similar trick. So what they did, instead of you know, this temperature profile, they changed it. What they did is can your volume be little bit raised, please? Mm, yeah, I think my volume is full only. Mm, actually, maybe you are getting this background noise. Uh, Oh, sorry. I did not mute myself. Anyway, I remember when I started, it was not mute. Anyway, so thank you for the reminder. But when did that happen? I don't recollect because I started with I checked this. Anyway, we'll continue. Uh, yeah, so these problems, I'm not sure when my voice stopped, but uh, so basically in this type of problems, what you do, you take the temperature profile, you differentiate it, put y equal to 0, and when you do that, you get del T by del y at y equal to 0, and then you calculate flux. Sometimes flux per unit temperature difference is required, sometimes only flux is required, like this problem, last problem that we did. Then you can play around. So they can give you different type of temperature profiles. For example, something like this, something like this. So, and one that we solved something like this. So it's up to you. I mean, as long as you know the trick, you'll solve them. You will not get stuck. Okay, and second set of problems from this topic is before going there, it's essentially this local heat transfer coefficient versus average heat transfer coefficient. So basically we use H for local heat transfer and H bar or H AVG for average heat transfer coefficient. So it's essentially, I mean, if you look into it, so basically this average heat transfer coefficient is nothing but 1 divided by cross sectional area or heat transfer surface area into the surface integral of your local uh, heat transfer coefficient into your incremental surface area. So this is the definition. Sometimes people say that, uh, how should I put it? Sometimes people define it something like this. They assume, let's say, some flat plate is there, something like this, and it is at constant wall temperature. There is some boundary layer developing like this. So let's say, and this is your length L. So what people do, they do the energy balance. So total heat, let's say, given this T wall is greater than T, so wall is giving the heat to the flowing fluid. So in that case, what is done is total energy balance will tell you uh, your average heat transfer coefficient into total area of the plate into T wall minus T infinity. This is total amount of heat coming out of the plate will be equal to the your local heat transfer coefficient into T wall, because your whole plate is at wall temperature, into dA, and from there usually this is the constant term gets cancelled and you get the same definition as this for the average heat transfer coefficient. This is okay, but this is a special case. I mean, there is a case where you're this thing, what you call, this plate is at not constant temperature. Let's say it is at constant flux. So you cannot define the average heat transfer coefficient this way for all cases. You should know that. This is its definition. By definition, it is defined like that, but it is this definition has not came from here. Is what I'm trying to say. This is okay. You can justify in one of the case when your full plate is at constant temperature, and then you'll end up with this formula for average heat transfer coefficient. But that is not the way where it came from, because I can give you that instead of constant wall temperature, I have constant heat flux. Then what you'll do? You'll not get this formula from that energy balance. I mean, by this I mean this formula. So like that. So that is one thing you should be aware, because in some mostly in some interviews people say that this comes from this, which is not totally correct. Okay, so very famous question from this is actually so far we have not talked about the scaling and etc. So we don't know, but very famous question is like this: for a flow over flat plate, h is proportional to the x power minus 1 by 2. X is distance from your starting point, leading edge. Then what is the ratio of average heat transfer coefficient to local heat transfer coefficient? So this is like very common question that is asked most of the time, and so you know you can uh, solve this like I mean this thing you should know, uh, so that's why I'm doing it. You can you know 1 second. Hmm. So now you use this formula because we know this is how the average heat transfer coefficient is defined. We know that average heat transfer coefficient is 1 by area into local heat transfer coefficient into surface area. We assume that the width of the flat plate is same, and in that case this area integral reduces to the uh, line integral, which is 0 to L h dx, because x is your leading coordinate, assuming constant width of flat plate. This is usually the case. Then you have to put x power minus 1 by 2 dx, and to do that, what you'll end up with is 1 by L x power 1 by 2 1 by 2 0 to L. Hmm. Actually, we should put some proportionality constant, right? Because this is proportional, so there will be some constant c. So like that we have to put, right? So there will be some c constant. It's a constant, so it will come out of integration. So now you have c by L. This is your L by 2. So basically your square root of L, and divided by 1 2, this becomes 2. So essentially you have 2 c by root L. Am I correct? Hmm. Now you put the 1 second. Actually, without fan, it's too hot. I'll switch on the fan. 1 second. Hmm. Yeah, where were we? at 1 by 2, so 2CL. Okay, yeah, I mean, we want the answer in terms of h, right? So we should not put the limits here, otherwise the whole thing reduces to L. So you know this is a surface integral. So till whatever x we are talking about, uh, like that we can consider this. So instead of putting in terms of L, because that will be like total. So you should put it something, up to some x. So then you'll get up to that x, what is your average heat transfer coefficient and what is the local heat transfer coefficient at that x. So if you do that, same thing again. So this C will come out of the integration and you will have 2 here and x power 1 by 2, like that, because 0 will be going to 0 and this limit will be there. So this is your h bar at that x, up to that x. And then this is nothing but 2c x power minus 1 by 2. And see, you know this c x power minus 1 by 2 is nothing but your h. So therefore, h bar is nothing but 2 times of your local heat transfer coefficient. So this is a very famous result. You should remember this. So up to any point x, if you have a local heat transfer coefficient of h there, then on an average till that point you will have average heat transfer coefficient which will be double of that h. So this is also very famous result. And again, I can this is typically this is true for typically laminar flows. We'll talk about this in next class or next discussion. But this can be anything. So we can have a note that what if, let's say, h local heat transfer coefficient is proportional to uh, you know some other power, let's say some x power minus n, where n can be fraction, integer, whatever it is, but positive thing. Then in that case, what happens? Your h bar will be nothing but again same thing, 1 by x, 0 to x, c x power minus n dx. So here you'll get 1 by x, c will be constant, so coming out. Then x power uh, minus n plus 1 divided by minus n plus 1 will be your integral, and there this will go away, and basically you will have something like this: c x power minus n divided by 1 minus n. So this denominator remains as it is. This guy, this x gets cancelled with this one, so you remain with x, c x power minus n, and that is nothing but your local heat transfer coefficient up to that point. So this can be your general solution also. So in this problem, since n, this is n, uh, so basically in last problem our n was 1 by 2, therefore your heat transfer, average heat transfer coefficient becomes 1 minus 1 by 2, which is nothing but 2 times the. So similarly, if in some other problem, if you find this as 1 by 3, then your average heat transfer coefficient will be 1 minus 1 by 3, so that will be 3 by 2 h, which is 1.5 times h. So like that. So this is a general solution to this kind of problem. Okay, that is one. And okay, and you should know one thing. Okay, so see, this is your this is your note number 1. Note number 2, which is actually pretty straightforward observation. So you have 1 minus 1 by n here, and your uh, local heat transfer coefficient. So you know n greater than 0, see, it should be less than 1 also, okay, otherwise it won't make any sense. So your uh, range for n should be 0 and less than 1. Then only this whole thing is valid. Otherwise, if it is negative, then it is not correct. So your end range is this one, and in that range, your denominator is always, so in this range, uh, I mean, it's basically math only. So if I multiply by -1 to this inequality, what I'll end up to with is minus n minus 1. Then what I do, add 1. So basically this becomes 1 minus 1, 0. So essentially the numerator always, this numerator is always between 0 to 1. Okay, so therefore this whole ratio, you know, I mean, this is nothing but 1 minus n less than 1. And if we take the inverse of this, uh, actually, I don't want to do it this way. See, the denominator is always less than 1 and in numerator you have 1. So, therefore, h bar will be always greater than h. So, what I am trying to say here is your average heat transfer coefficient will always be greater than your local heat transfer coefficient. That is also sometimes asked. Okay, so this is there. Yeah. Yeah, and sometimes what happens, there can be two options. For example, let's say there is something like this, a flat plate, which is fairly long. So, sorry. So you will have something like this, then some transition, and then some other. So basically, laminar turbulent, that game. So what happens? We'll not talk about it. I mean, yeah, sir introduced laminar turbulent, right? So till this point, maybe from, let's say, if this is your 0 to L1, this is laminar flow, and then from here, let's say it becomes uh, turbulent flow. So till, let's say, L2. So in that case, uh, you have to divide this integral, because you cannot just put 0 to this thing, right? So in that case, what you have to do is your average heat transfer coefficient becomes 1 by L1. I mean, I'm talking about for whole plate, okay, not any x. So that's why I'm taking L here. So you have to integrate from 0 to L1. Then whatever is the laminar heat transfer coefficient relation is there, you have to use that as a function of x. Then from next, uh, for the remaining length, which is L2 minus L1, this is the length over which the flow is in turbulent regime, and then you have to integrate it from L1 to L2, and then again you have to use turbulent heat transfer coefficient scaling or relation, and then you have to do that. So usually in most of the problems you will be okay with only using one integration, but in some cases they will ask you to use multiple integrations, like that it may happen. Okay, so you should be aware of those. Yeah, I think this is most of the discussion on laminar turbulent, I mean average heat transfer coefficient, etc. Scaling and all will take in next class. I don't want to start now because it is itself is a good uh, you know problem itself. So before going there, yeah, we can take one more question. Then maybe we can take some different type of question. So 1 second. Okay, so we'll take one question. Yeah, somebody joined the chat and left. Anyway, I think some network issue. I'll just drink some water. See, basically we are coming back to the same thing only. But okay, we'll take this problem. Okay, so again, there is a flat plate. There is a flow over it, and you have some boundary layer developing. This U infinity, T infinity are your what you call free stream velocities. Your plate is at 90 degrees, and your infinity temperature or the ambient temperature is around 20 degrees. The question is, if your temperature profile is a function of x and y now, typically it is not the case. That's why this problem is okay. I'm just changing the number. It is from a book, so I'll just simplify the number. So it will be something like 10 plus 20 exponential minus 40 xy, or you can take x square into y. So x is your this direction and y is your vertical direction. So basically they have given some complicated temperature distribution function within the boundary layer, and find expression for average heat transfer coefficient at some point x in the boundary layer. So from previous problems we know that local heat transfer coefficient we can calculate from k del t by del y at y equal to 0 divided by t wall minus t infinity. Okay, so this will be minus k. Now we have to take dt by dy, so the constant will go away. So now see, the thing is it's an exponential function, right? So you have to differentiate carefully. This term will remain as it is, minus 40 into x square y, and now we have to differentiate the inner term with respect to y. So that will give you minus 40 into x square. Y will be 1. Okay, and this you have to evaluate at y equal to 0. This term, the whole term, and divided by t wall minus t infinity as it is. So when you put y equal to 0, this term goes to 1. So what you are what you are left with is minus k into 20 into minus 40 x square, and this t wall minus t infinity is nothing but 90 minus 20, so this is 70. I should not write this. So if you simplify, you will get what, 80 by 7, something like that, no? So 80kx square by 7. Okay, so this is your heat transfer coefficient at local heat transfer coefficient at some location x from the leading edge. Now you need to find the average heat transfer coefficient. So that will be 1 by x hx dx. So till that location we are finding, not for the whole plate. So that will be 1 by x. Now this 80k by 7 is constant, and x square integration is x cube by 3. So you have x cube by 3 here. Therefore you have 80x square k by 21 as your average heat transfer coefficient expression. So if k is the thermal conductivity of fluid, if that is given, you can put, but in this question it was not. So similar approach you have to follow is what I'm trying to say. Now let me see if we can take some another type of problem. I don't want to take the what they call boundary layer related or scaling related problems this time. We'll do that next time. So let me just see if I can find some problems. Yeah, I mean, there is a problem there, but it's not strictly related to average heat transfer coefficient, etc. One second. Okay. Okay, so what else is there? Yeah, sometimes, till now we were discussing about the flat plates. Sometimes what they'll do, they'll give you something which is like rotatory or something like that. I think in your assignments for week 4, there are some problems like that, in which you'll have a rotating plate and there will be some distribution of your heat transfer coefficient on that plate, and then you need to find what's happening there, something like that. So what I mean is, one second. Yeah, I think I mean, I don't want to solve the whole problem, because in your assignment only I saw some question like this. Yeah, problem number 5. Then second problem. Yeah, see, the due date is tomorrow. Anyway, maybe we can look into this. It's not like. Okay, so we'll solve that because you'll have similar problems there only. So, okay, I'll solve that problem only. Maybe we'll do some simplification. But anyway, I think people will not see this lecture who are not attending by tomorrow. So those who are attending, let them get some benefit out of this. So yeah, so what they are saying here is there is a plate, circular plate with radius R0 and temperature Ts. Gas flow over the plate axisymmetric, causing local convection. Okay, determine the rate of heat transfer. Okay, so basically, I'll just give you a simple trick or the way to solve this type of problems. Let's say if this is your plate and let's say this is your rotating with some angular velocity omega and some plate temperature as Ts infinity as T infinity and some heat transfer is happening between them. Uh, what happens in this case, your local heat transfer coefficient becomes function of radius, or not radius I should not say, but some radial location, radial coordinate. And then they will ask you, to find average heat flux at some rate location R, or some flux at location R, or total heat flux uh, transferring from plate to ambient or ambient to plate depending on uh, the direction of heat flow. So the trick here is, see, if you want to find, average heat transfer coefficient till some radius R, the formula is same, 1 by A local heat transfer coefficient, which is function of R into uh, you have to take dA. But here, your dA will become, function of R. So typically dA is nothing but 2 pi R dr. We know that, right? We take a small strip on the, uh, what you call, if you look at this surface from the top. 1 second. Yeah, so if you look at this disk from top, it will look like a circle. And if you want to take a small strip here, something like this. So from center here at R location, and this thickness is dr. So your dA is nothing but 2 pi r dr, and your A is pi r square. Correct, no? So you have to use that trick. So coming back to this second question of the assignment, uh, here they have given the function of H, you know. So let's say if your heat transfer coefficient is function of some constants and r to the power n, where a, b, and n are constant, and your maximum plate radius is r0, that is your radius of the plate. So you have to find, and plate is at Ts and your ambient is at T infinity. You need to find the rate of heat transfer. So convection, to find Q convection. So we know from basic energy balance will be nothing but integration of heat transferred from a strip into this uh, elemental area. Correct, no? So whatever heat is getting transferred from uh, this small strip of dA cross sectional area, that will be your and this will be flux, because we are multiplying flux with the area, right? So that's why that will give you total Q. So if that is the case, now we know that Q the flux will be nothing but HR into Ts minus T infinity, because the whole plate is at Ts, so your small strip will also be at Ts. So therefore your Q convection is nothing but integration of HR Ts minus T infinity into dA. So dA is nothing but 2 pi r dr. Correct, no? So now HR is function which is given by this correlation. There can be anything. In this problem it is like this, so we'll use that. And this guy is constant, so it will come out of integration, the delta T. So you will have Ts minus T infinity outside. You will have 0 to R naught, because the whole plate we have to consider. HR is A plus B R power n into 2 pi R dr. So 2 pi also is constant, so we'll take that out also. Otherwise, every time we have to write. So this will be like the case. So what we'll do, we'll solve this integral and we'll put this constant last time. So this is 0 to R naught AR plus B R power n plus 1 into dr. Now you do the integration. So first term is, I should write this way. A will come out of the constant. R integration is R square by 2, 0 to R naught. B will come out. R n plus 1 integration is R n plus 2 by n plus 2, 0 to R naught. So at 0, R everything goes to 0. So you end up basically with A R naught square by 2 plus B R naught n plus 2 power divided by n plus 2. So this is your integration, and you put that back in the convection term. So your Q convection is 2 pi Ts minus T infinity A R naught square by 2 plus B R naught n plus 2 power divided by n plus 2, bracket complete. So now what options we have here? Yeah, I think now you can see, right, which option is correct. So here I have taken Ts minus T infinity, assuming Ts is greater than T infinity, but I think in problem it is ulta. Yeah, hot gas jet T infinity is greater than Ts, so I mean, you understand, right? Only this term will change, but the remaining thing is same, so you can figure it out. I mean, there is nothing to figure out. The solution is right in front of you. I hope it is clear now. So like that you have to see. Okay. What else is there? What about fifth problem? Fifth problem, so it's, you know, it's simple, no? Because see here, so in fifth problem, what they have done is same. It is a cylindrical circular disc, and it is rotating about its y-axis or z-axis. No, I think y. Yeah, in figure it is y. So there is a small thickness of fluid on the top of it, which is flowing over it. Here they have mentioned your heat transfer coefficient is a constant, and it is equal to 20 watt per meter square Kelvin. Ambient temperature is T infinity, 20 degrees Celsius. What else? The plate temperature is 50 degrees Celsius, which is constant, because there is a heater inside that plate, which is making it at higher temperature than ambient. You have the heat transfer coefficient as, oh, it is given, sorry. The radius, of the plate is around 100 mm, and then what they have asked is, what is the local heat flux at the surface of disk? What is the total electric power requirement? So we have a formula for flux, which is H at any distance R into T plate or surface minus T infinity. So here your h is constant, which is 20, so it is not changing with radius, and your delta T is 50 minus 20, so that is 20 into 30, so your flux is 600 watt per meter square. And what is the next part? What is the total electric power requirement? So total power is integration of flux, or you can just multiply here because h is constant, right? Your flux is constant. You can just multiply this flux with area, so the plate area, so that will be pi r naught square. This is possible because your flux is not function of r, so directly you can multiply with area and you should get the thing. So what will be 600 into pi into r naught. R naught is 100 mm, so 0.1. So 0.1 square. So that is 10 to the power minus 2. So 6 pi. 6 pi is something around 18. 18 point, I think there is a, this 18.9 is the correct, I think. Yeah. Okay. 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 What else is there? Yeah, we'll take one problem from this mass transfer, because major discussion is focused on heat transfer, because that is the main part of the course. But you can use the same similar analogies in mass transfer also, and we'll take one problem for that, and maybe after that we'll stop for today. So yeah, one thing. Let me just see if I have missed anything or not. Nah. So yeah, I mean there are two problems, but let's go with the mass transfer. So fourth problem is also difficult. Yeah, I mean fourth problem, I think there is something missing there. I saw. I mean, maybe next time I'll come back to that, because anyway we are at the end of the class. Uh, they have given the bearing and mu as the viscosity, K as the conductivity, and both are at 40 degrees. So see, as far as I can understand, what is the maximum temperature in the oil when the journal is rotating at 10 meters per second? See, third option will not be there, I think, because it is equal to 40. So C option is not there. D option looks very high. So if I have to guess, it should be option A, 40.8, or maybe option D. But yeah, exactly how to solve this, because I don't think this is related to convection. Maybe I'm missing something. I'll get back to you on this maybe in the next class, because I have a doubt that this requires something else. Maybe governing equations, I don't know. Usually what happens when you have this journal bearing problems, they give you clearance and you assume linear velocity profile and you solve those problems. But here they have not given anything. So what can be the thing? velocity is given. Okay. Assume steady state v square by del u by del x. 1 second, I'll think about it. I think we have to go from basic governing equations of this type of problem. Rho Cp u del t by del y is nothing but they have not mentioned del square t by del y square. 1 second. I think you have to solve this using governing equations. I think professor discussed in the last class, I think, energy balance. 1 second, I just have to see, because they have only given what you call, you know, see, mu Cp by K, I mean, even if you write energy balance, see, rho Cp u del t by del x, or it will be R. But they have not given Cp also, right? Not density, so you can't use those. No, I think there is something wrong or something is missing in this question. I'm not able to figure out right now, because they have only given you as mu and okay. Yeah, sorry, but I think there is something which is off about this question. Because only K and mu are given. So if you only have those two things, what can you do with this? You have velocity, you don't have rho Cp. Concession, I'm not sure about this, because there will be, see, this is all automated. It won't be manually done. So what they'll do is they'll give marks for each question and then they'll evaluate like that. I'm not sure about what happens when the question is wrong or incomplete, something like what we are facing right now. You do one thing. I have to think about this because there is something which is missing here. So what we'll do, see, I have to upload these notes by tonight anyway. So after the class, I'll think about this, and maybe by tonight, if I find the answer, I'll upload it. Otherwise, next class is the only solution. Because right now, I think there is something missing here. Because only velocity, mu, and k are given. No rho, no Cp. See, I think you can put option A as the most probable answer. Because otherwise, other options are very anyway. So Yeah, I'll try to give the answer in the notes by tonight, but right now I think I'm not able to get it because there is something which is off, because both are at 40 degrees. So even if you assume it as a flat plate, you can't do. Uh, if it is 40, see, I know you have to use Navier-Stokes in radial coordinate system for this, if that is the case. Uh, but for that you need some other information, right? Because we will have some. Yeah, I mean, maybe energy equation if you apply in radial coordinates only in r direction. But see, they have not mentioned any gap or any radius. Anything is not there. Uh, so I'm not sure whether this is correct. Something should be there. Mm, okay, I'll try to solve this by tonight if possible. Otherwise, next class we'll see. So we'll move on. I wanted to take one mass transfer problem. Uh, so because typically we don't discuss mass transfer much, uh, because on the contrary it's very important. We don't discuss, that's another case, but it's there. So basically uh, there is a boundary, solid boundary, and you have a fluid layer or water layer, I think. Yeah, yeah, it is a water layer lying on that boundary. And what is happening is uh, some height is there. Okay, height is not given, but okay, anyway, uh, the it is getting evaporated. So this liquid water is being evaporated, and it is going out in the air. So there is air outside, which is at uh, how much? 1 second. This water is at 305 Kelvin, and air is also at 305 Kelvin. So there is no temperature difference. So there is only concentration difference. And the air is flowing on top of the water layer, and air has some 40% of what you call relative humidity. So this is not a dry air. There is some humidity there, relative humidity in the air. And this, they have not mentioned the height, but they have given the rate at which this height is decreasing, which is called as recession rate. So here we'll represent this height by capital H. So they have given dH by dt, rate of change of height, as 0.1 mm per hour. So it's a slow process, and the negative sign implies it is evaporating. So the water is going out basically. Uh, yeah, I think it is 0.11 mm, 11. Okay. So and density of liquid water is given as 995 kg per meter cube, and density of saturated vapor at 305 Kelvin is given as 0.0336 kg per meter cube. So all this information is given in the problem. I hope the problem is clear. What is happening is there is a water layer on top of a solid surface, something like we observe most of the times. Air is flowing on top of it at this much temperature and relative humidity, and because of that, water vapor is getting evaporated, and the rate of evaporation is this much. and some density and all are given. So now you need to find what is the rate at which mass is lost because of evaporation per unit surface area. So first part is what is the rate at which liquid water mass is lost due to evaporation per unit surface area. So first of all we need to find some quantity whose unit will be kg per meter square per second, right? Because the rate of mass loss is kg per second and per unit area it's kg per meter square per second. So that is one thing that I think of it as soon as I see this problem. So now you have to apply a control volume analysis. So take this water as a control volume. So if you do that and apply conservation of species to the control volume, what you can say, or even you can say applying mass conservation, because there is only one species, not one species, but like there is a phase change here, but it's all water, it's getting converted into liquid to vapor, but mass conservation will still hold. You can call it species, mass, whatever you want. So by that logic, by applying conservation of species to the control volume, we can write rate at which liquid water evaporates is equal to rate at which volume of liquid water decreases. Correct, no? So now we know this, right? Rate at which water is volume of water is decreasing. That is nothing but d by dt of mass of liquid water. And what is the mass? We can write it in terms of density. Density of liquid water into volume of the this pool. Now see, we don't know the area. They have not mentioned any surface area or anything like that. So let it be. We'll write it like this: rho of liquid water into some area into the height, and we have dH by dt, right? So we'll assume constant area. But here we'll have some rate of evaporation for mass into area, because that is where the evaporation is happening, right? And there will be a negative sign here, because uh, you can put negative sign anywhere, because see, you are considering a control volume and the water is leaving your control volume, so maybe you can put the negative sign over here. It doesn't matter, as long as you understand why we are putting it here. So now then this area gets cancelled because it's constant area. The surface area is not changing, the height is changing. And therefore you get m dot, the rate at which water vapor is evaporating is nothing but rho of liquid water into dH by dt with negative sign. And if you put the numbers, negative 995 is the density of liquid water, and dH by dt is this recession rate, right? So this is minus 0.11, but that is in mm per hour, right? So mm you have to convert into meter, minus 3, and you have to divide by 3600. So you will have everything in standard units. So if you do this calculation, you should get 2.76 into 10 to the power minus 5 kg per meter square second. So this is your answer to this first part of the question. So basic mass conservation or species conservation only we have applied here, nothing fancy. But one thing you should note is, see, this unit we expected and we are getting in this unit only. You can, do simple thing. So density is kg per meter cube, and this rate of change is meter per second. So this becomes meter per second. So correct. It's always good to have some dimensional correctness check also many times. And then the second part of the question is, what is the convection mass transfer coefficient? So here they have just mentioned as what is the convection mass transfer coefficient. Typically in class, sir was using this H subscript M symbol for it, but nothing is mentioned, so this will be average coefficient. You can't say it's local or something, it's average for whole control volume, because otherwise there is no information. And whatever is evaporating, that is evaporating, and then basically that is what we have to use as the, see, basically in heat transfer, what you do, the heat transfer rate is heat transfer coefficient into area into delta T. Here, since we are talking about flux, the area term is already incorporated. So basically, I am just drawing the analogy. In case of heat transfer, this term is proportional to the heat transfer flux divided by delta T, right? So similarly here, this will be proportional to the mass transfer flux and divided by the concentration gradient. Correct, no? So this is concentration gradient, because as for heat transfer you have to have temperature gradient, for mass transfer you must have concentration gradient, otherwise you can't have mass transfer. Yeah, so like that. Now typically this is concentration, not gradient, I should not say, it's different. So typically concentration is mole per meter cube, that is like typical unit for concentration. But here we have this relative humidity, right? They have not given us in moles and all. So now we need to find this. You can use exact sign only, because this is the definition itself. I should not say proportional. This should be exactly same. That is the definition of average heat transfer and mass transfer coefficients. Now these concentrations are in mole, should be in mole per meter cube. I mean, usually they are. How to get that? Or you can have in kg per meter cube. Anything is fine as long as it is in standard SI units. here this quantity in kg per meter square second, right? So concentration, it is better if we take in kg per meter cube. So now the concentration. So what is the concentration difference? See, see here the relative humidity is 40%, and this water is saturated liquid water, right? Then only evaporation is taking place, and that density is this much. So what you can do, you can assume this as 100% liquid water, or at interface basically when it is convection. So at interface you will have 100% saturated vapor, and that is getting convected into air, which is at 40%. So your concentration difference is coming from the relative humidity difference. So that you can take your saturated vapor density here, because as sir also said in the one of the class in the previous week's lectures, we consider concentration at the surface, not at the bulk. Okay, so since we are considering water vapor going out, here you have to consider concentration of water vapor at the boundary of the control volume, and that will be multiplied by 1 minus 0.4. So 1 is like 100% water vapor and 0.4 is 40% water vapor, and this whole thing is given. So this we calculated in the first part, and density of this is 0.0, I think 336 or something like that. 336 into 0.6. So if you calculate, you should get 1.37 into 10 to the power minus 3 meter per second. So this is the solution, but I think more than that you should note one thing, which is note the units for the mass transfer coefficient are meter per second. This is very important, because for heat transfer coefficient the units are watt per meter square Kelvin. Here it is not so. So if you don't know the units, it will be very tough for first time if you want to solve this problem, because once you get answer in something like this term, you will be wondering whether I did correct or is there anything wrong. But keep in mind the mass transfer coefficient has units of meter per second, which is velocity units. I mean, not velocity, it's velocity units also. And our heat transfer coefficient is different. So this is about this. I think today we can stop here, because other than that one question, assignment question number 4, I think other problems you can solve more or less. There are very important things about this bound layer, etc., but that I think comes later. Next class we'll discuss those in great detail, scaling, etc. Everything is there. So today we'll stop here only. I'll try to get the answer for that assignment question by tonight. If you see that in my notes, which I'll upload later, well and good. Otherwise, we'll have to see this next week. Okay, so we'll stop here. There are some other questions, but I think you can manage with what we discussed today. Yeah, more or less similar only. Yeah, I think it's there. Okay then. Yeah. Yeah. Thank you. And see you next time. I'll close the meeting. Okay. Thank you. Good night.